I am Jean-Marie Furbringer. I'm lecturer at the Swiss Federal Institute of Technology. The objective of the present today is to show you what design of experiment, called DOE, can bring to research and development. The world is noisy, multifactorial, and cause have interaction between them. Design of experiment have been tailored especially for this situation to confront this challenge. DOE foster efficiency in research and development thanks to its multifactorial perspective. DOE allows to determine interactions between factors in a simple and economical way. DOE support an iterative approach of experimental endeavors. So it's the opportunity to improve the quality of your data by having smaller confidence interval. You will increase the speed between your experiment and getting the results and eventually going to the market. The result will be of better quality, will be more comprehensive, and then diminishing the numbers of experiments, you can reduce the cost. With two examples, I will illustrate that. So the first example that I've called a Pareto analysis is showing how interactions are key element in the analysis of an experimental situation. These schemes present the different factors we have in a given situation, let's say 5 factors, and so we have the effect of the factors we call main effect. But we can also have the interaction. That means that the responses that we are checking will depend not only on the value of, in this case, 1 and 2, but also on the common value of the both. If they are in the highest position, in the smallest position, it will have an influence on one in the highest, one in the lowest position will have an influence. So imagine a case, we have a device, we are producing a device. Imagine that we are doing the technology validation phase and we would like to increase the life duration of our device. Is the responses that we have. And we have a few factors that we can change. We eventually can change the width of one of the elements, the radius of another element. We have 2 volumes that we can change, and we have a temperature that we can change in our device. So let's see how we can determine what are the important factors and what are the important interactions, and to do everything we can to improve the device. We have then 5 factors, and we have one answer, which is the life duration of the device. So when we are faced to such a situation, we can use something that is called the empirical models. We can make the first hypothesis that, in fact, we just have a constant. That means that there are no influence of our factors, and we have a constant as a response, and we have some errors when we are making measurement. This will represent an hyperplane which is flat. Very probably, it's most interesting that we will have some main influence. We call those main effects, and it will correspond to the first graphic, which is here. We will have an hyperplane, and determining the effects will be determining the slope of each of the factors, which of the direction. Perhaps it's a little bit more complicated situation, and we have interactions, which are written here in green. It represents the model which is here in the center, and it consists in a hyperplane which is twisted. Fourth hypothesis would be that we do not only have main effects, interactions, but also we could have curvature. So, for example, second degree curvature for our model, and then we will have a surface which will look like this. Is represented here in 2 dimensions, but we can have in many dimensions, or typically in 5 dimensions, as it is our case. So if we would like to represent our situation with our device with interactions, That means that we will have 16 coefficients, and the model can be expressed as it is written here. We have a constant, we will have main effect, and we will have a few tens in reality of instructions coefficients that sum up the influence of the factors 2 by 2. So for determining all those coefficients, we have what is called designs that are already known from the theory. And here you have in front of you a map that can be used for choosing what we have. We have the numbers of factors that are distributed horizontally, you see, between 1 and 11. We can even imagine more, but this table is still 11 factors. And we have vertically the number of experiments. So in our case, we are with 5 factors. So I see 2 possibilities. We could have a factorial design, 2 power 5, with 32 experiments, or we can have, in this situation, a fractional factorial design, 2 power 5 minus 1, which has 16 experiments, so half of the full factorial design. This design is also indicated with a small 5 in Roman numbers, indicating that the resolution is of level 5. That means that we will mix 2 by 2 factors with 3 by 3 interactions. We will also mix main effect with 4 level interactions. So it's very interesting. That means that all our 2 by 2 interactions that interest us will not be mixed together. So the design, what we propose, the 2 power 5 minus 1 with the resolution 5, is represented here. You see 4 cubes, and each of these cubes represent a 3-dimensional space. So for going to the 4th dimension, that means that we have to go from left to right, and for going to the 5th dimension, we go from up to down. So these 4 cubes represent schematically a 5-dimension space. And the experiments that we will realize experiments at the extreme of our factors. They are represented by the red dots. So you see that in each of the cubes we are representing 4 experiments. So in total it would mean 16 experiments. So if we realize these 16 experiments, we can determine the 16 coefficient of our model. It will have a very interesting variance level, so it will be the variance of the experiment, sigma squared, divided by 16. Why that? Because in fact, when we will make the effect, when we will calculate the effect, we will have all the 16 experiments able to make this calculation of the effect. So it will be more powerful than if we do one factor at a time experiment. So imagine we have made the experiment, we have used a least square fit algorithm for getting all the coefficients, and then we can represent them. They are ordered from the most important at left to the less important at right, and you can see that the most important one is the factor 3. After we have the interaction between 1 and 2, which seems to be important, it's negative. That means that when we have the product of 1 and 2, which is at both at the minimum, that we will have the maximum effect. We will then have factor 5, factor 1, factor 2, factor 4, after we have interaction 1 and 3, 1 and 4, etc., etc. So I'm explaining now to what it corresponds the left-hand side scale. And so each of these bars, the blue bars, are representing what we call the half effect. They are half effect because we are from the center to one of the extreme of the domain of the different factors of the different interactions. So some are positive and some are negative as said. So we can cumulate them to check how far we can go for improving our device. It is the purple line, which is here. But we have interactions That means that we will perhaps not be able to take profit of all of the effects. For having the maximum related to the factor 3, we see that we have the effect A3 positive. That means that if I'm taking the highest value for the factor 3, I will profit of this improvement. For the interaction 1, 2, I have to take into consideration the value of 1 and 2. But the main effect 1 and 2 are smaller than the interaction. So it's the interaction that is dominating the process. And that means that if I want to take profit of this, I need to have a negative factor for multiplying this negative effect, because minus by minus made plus. So that means that I need having one of the factor positive or at the maximum and one of the factor at the minimum. So I will do that by choosing which one I will take positive or negative between A1 and A2. But they are both negative. So if I take one positive, one negative, that means that I will miss one of them. So I will choose the first one as negative, or understand as at the minimum value, and the other at the positive. It's why the red curve here is decreasing, because I was able to profit of the factor A1, of the coefficient of the factor A1, but I was not able to profit of the factor A2 because I wanted to take profit of the interaction of A1 and A2. And so, like that, you see with a sort of Pareto diagram, integrating the interaction, I'm really able to understand how I will be able to improve at the maximum my device. So it's time to have a conclusion of this simple case. You can see that interaction is playing a key role in this analysis and the management of this process. In this case, the use of the DOE technique brings efficiency in terms of determining the interaction and permitting a smart Pareto analysis. You see that the answer, which is represented by Y here, is influenced directly by two of the factors, but we have three factors, 1, 2, and 3, that influence this directly and indirectly too, because we have two interactions. So the determination of the interactions have allowed us to have a bigger insight in our phenomena. So the choice of the adequate design lets us minimizing also the numbers of experiments. If I have used the factorial design, it would have been 32 experiments, and I was able to do that for half of the work with only 16 experiments. Finally, let's say something about the expertise that which is necessary for doing that. Fractional factorial design is like a sort of mechanics, and you need to know it. So it's important to know design of experiment, to follow some training in this subject for being able to take profit of this theory. Last example to illustrate how DOE can help to follow an iterative strategy. An iterative strategy with the idea that we start with a small effect and we can go with a better quality at the end of our process. The interest of iterative strategy is because at the end of one experiment we know a lot more than we knew at the beginning. So it's the right moment for designing the experiment. So having iterative strategy, let's have part of experiment, analyzing what we have and take a better decision for the next steps. Imagine a case in which we have a chamber and we would like to depose monoatomic layers on a substrate of silicium. So for doing that, we have to manage many factors. Imagine that 7 among those factors are important, and you can accept that 7 factors is already quite a lot of factors to manage. We would have the concentration of the gas 1, we could have the concentration of a second gas, we could have 3 temperatures for the factors 3, 4, and 5, and we could have delay between the phase 1 and the phase 2, and delay between phase 2 and phase 4. Where are those important effects are coming from? They can come from the literature, they can come from the previous experiments that you would have made, your expertise in the subject. We can follow a series of steps. The first step would be a screening. That means that as we have 7 factors, which is a lot, we will see if it's possible to get rid of some of them. It's also called the Pareto analysis. Sometimes it is done conceptually with some calculation, with the physics, with the electronics of the situation. Sometimes it's done with experiment. It's what I want to show you here. We have what is called screening designs that have been tailored especially for this situation. Most famous of them is the Plackett-Burman design. With n runs, imagine for example 4 runs, we can analyze n-1 factors. So, for example, with 4 experiments, we can analyze 3 factors. With 8 experiments, we can analyze till 7 factors. We can also get rid of eventual interactions, because all the time the question is, do we have interactions or not? When we do not have interaction, we can go straight forward. If we have interaction, we perhaps want to get rid of interactions, and we can do that with a technique which is called fold over. We will redo the Plackett-Burman design, but we will inverse the value of the factors. When the factors were used at the highest position, we will use them at the smallest position and the lowest position, and when we have used it at the lowest position, we will use it now with the highest position. You can see in the graphic that you have the blue bars representing what we get with the Plackett-Burman design. You see that we have a main effect, which is important, and after we have a few effects. It happens that it's the 3 first effects that are important. In red is what we have obtained with the fold-over design. That means that we have redo quite the same experiment reversed. And you see some difference. So this difference, first, which is nice in this situation, we see that it's the same factor that seems important, and then this small difference are indicating that in fact we have a few interactions. So we have been able to eliminate a part of our factors. We now have just 3 of them, but we also understand that we have some interactions. So we can go to a second step. The second step will consist in performing a fractional factorial design, because we want to determine the interactions 2 by 2 at least. So we have a collection that I showed previously of design called 2 power n minus p that are fraction of a full factorial design. So we can realize this design, then analyze the effects that we have. And when we have that, we do that through what is called a probability plot, because we do not have 3 degrees of freedom for making an ANOVA or something like that. So what we want to check if what are the important factors and the important interactions. So you can see with this graphic that we have been able to detect that the 3 first factors are important, 1, 2, and 3. And we also have detected that we have 3, we call them contrasts. We have 3 mixture of coefficients 2 by 2 that are important. And we have a series of coefficients that are not important at all. They are in a straight line because it's a normal plot, and in normal plot we are checking if the values of our coefficients are related to the normal distribution. And if you check in the upper part of the right hand side, you can see what are those contrasts, and you see that in the contrast C1 we have several things, but we have the interaction 1 and 2. In the C2 we have 1 and 3, and in C4 we have 2 and 3. And this is confirming that very, very probably the most important factors are 1, 2, and 3, and the interactions related to this 3 factor. So this would be finish the step 2. In a third step, we could be interested to discover if we have curvature, because this curvature will help us to go to a maximum. So to the red dots that we already have done previously, we can add some points at the center of the domain and some points which are in blue in this graphic that represent measurements that are placed more or less at the center of the faces of our cube, or it could be an hypercube if we have more than 3 dimensions. So with making those measurements, we will be now able to identify a second degree model and then to discover what could be the shape. And in the second degree model, the shape are not a mystery. That can be an ellipsoid, or it could be an hyperboloid. So an ellipsoid is a sort of rugby ball. So it's what we have done. We have done the measurement represented here with the blue and red dots and the dots of other color. And we have obtained a second degree model, and we have performed a canonical analysis. And the canonical analysis is exactly precising the geometry of the response. And you can see in the graphic on the right-hand side that we have something as a rugby ball. So we are in an ellipsoid model. And as we are trying to maximize some property of our device, it's at the center of this figure that are the maximum. So very probably the maximum are related in a point somewhere here, and we can have maximum evolving on the axis of this ellipsoid. So if we want to make a small conclusion of this case, you see that the best moment for planning an action is at the end of a previous action. So it's why it's very interesting to apply an iterative strategy. So it's let us improve the information that we have step by step. The iteration can be on the complexity of the model, as here. So we have first a linear model with interaction, and after a second degree model, and we could continue. Sometimes it could be also on the number of factors that we are considering. We have designed with which we can start with a few factors and step by step add new factors for trying to understand how they influence the picture that we have obtained previously. So in this case, we have start with screening. After we have made an analysis of the interaction, after we have analysis of second degree, and we can finally finish with an optimization. It's a very standard iterative process for analyzing an industrial process. So now we can arrive to a general conclusion about the interest of DOE for research and development. Nature answers questions very narrowly. So it's very important to have very sharp questions, and DOE will help you to sharp your questions. Why? Because we are using a multifactorial approach. It's let us like that diminish the confidence interval of the results. It's also help to noise reduction, and we are also taking interaction into account. If you do that without design experiment, it will take you a lot of time. The one factor at a time strategy is sure. It is used quite in a lot of laboratory. It's sure, but it's very long and finally very costly. So the interest of using DOE is in the fact that you would improve the quality of your data, you will speed up your research, and you will have results of better quality, diminishing your cost because you are reducing the numbers of experiments necessary for getting a result. So here are a few references. The Bible in the subject is a book by Box. The book by Montgomery that teaches the subject in American university is also very good. Recently, Mr. Ryan have made a new approach, a modern approach. It also can bring new perspective on what have been done by the fathers. And this is also sometimes used in sensitivity analysis of numerical model. Is why I've put also a false reference on numerical simulation. So thank you very much for your attention. I hope this interests you. Bye-bye.